So we're going to use derivatives of exponential and logarithm functions to solve some problems. And then at the very end today, what we're going to do is it's called logarithmic differentiation. Okay. So right off the get-go, all right, we have this problem. At what point on the graph of y equals 2 to the x minus 3, so this is an exponential function, all right, and so we want, is the tangent line parallel to y equals 21x plus 4? So we want a tangent line to this. Well, if we want a tangent line, right, then we want to find the derivative, and we want it to be, that tangent line, whatever it is, to be parallel to this one. So the slopes of our tangent line and the slope of this line have to be the same to be parallel, okay? So parallel lines have the same slope. That's one of the facts that we need to remember, okay? Parallel lines have the same slope. All right, so we want to find dy over dx. And so we want to take the derivative of this. Well, the derivative of 2 to the x is 2 to the x, remember, times the natural log of 2. Well, that's the slope of any point, okay? That's the slope at any point on this curve. Well, we want our line to be parallel to this one, so we want this dy over dx to equal 21. So that means 2 to the x times the natural log of 2 is equal to 21. So now it's a matter of solving this, okay? So I want to get this 2 to the x by itself, so I'm multiplying by natural log of 2. So I'm just going to divide both sides by natural log of 2. So this would give me 2 to the x is equal to 21 divided by the natural log of 2. So now what I'm going to do is I need to get this variable out of the exponent. So what I'm going to do is I'm going to take the natural log of both sides. So ln of 2 to the x is equal to ln of 21 over ln of 2. Yeah, we have a natural log within a natural log, right? Okay, now I'm going to use logarithm properties that says if you're taking the logarithm of something raised to a power, you can rewrite that as the power times the natural log of this base. So this can be rewritten as x times the natural log of 2 is equal to the natural log of 21 over the natural log of 2. And now to get x by itself, all I need to do is divide both sides by this natural log of 2. So x is equal to the natural log of 21 over the natural log of 2 all over the natural log of 2. Now we can use logarithm properties because if you take the log of a quotient, that's the log of the numerator minus the log of the denominator. So we can actually rewrite this, and x is equal to the natural log of 21 minus the natural log of the denominator, which would be the natural log of 2, all over the natural log of 2. This is just a little bit easier to put into our calculator, okay? So I'm going to put this into our calculator, and I'll come back. So we want to press the fraction bar, and then the natural log of 21, and then close the parenthesis, and then minus ln of 2, then close the parenthesis for the inner natural log and close the parenthesis for the outer natural log, and then go down to the denominator and then type in ln 2. And we get 4.921. So from our graphing calculator, what we got was approximately an x value of 4.921. Now, I'm asking you for the point, which means I also need to know the y coordinate, all right? So we know we can find the y coordinate, all right, because we know that y is equal to 2 to the x minus 3. Here's my x. Now, I wouldn't put this in because we'd have some rounding error probably. I would put this in, okay? So this becomes y is equal to 2 raised to the natural log of 21 minus the natural log of the natural log of 2 over the natural log of 2. And that's my exponent. And then I need to come down out of the exponent and subtract 3. So I'm going to go to my graphing calculator and I'm going to put this in and then we'll come back. And then we can type 2 and then raise to the, and then we can go up and press enter. Okay, so and you just highlight what you want to do and then you can paste it where you want it. Now, right now I'm in the exponent, so I want to come down. So I'm going to do the right arrow and then I want to do minus 3 and we'll have our y value, which is 27.297. So after putting that into my graphing calculator, I get y is about 27.297. So the point on this curve that has a tangent line that's parallel to this would be at the point 4.921, comma 27.297. All right, let's go to the next problem. So find f prime of x and state the domain of f prime of x if f of x is equal to ln of x minus 7. So domain, the very first thing is what the argument is, which is what we're taking the log of, right? In this case, it's x minus 7. X minus 7 must always be positive. So x minus 7 is greater than 0, which means x is greater than 7. All right. So now because of that, we're going to take the derivative. So f prime of x is equal to 1 over x minus 7 times the derivative of the inside here, which would just be dx over dx, which is 1, right? So that's it. It's 1 over x minus 7. Now the domain for this, and I would just write with inequalities, is this. X has to be greater than 7. Because anything outside of this, it's going to either make it, like if it's exactly 7, that's a big problem automatically because it's going to make the denominator 0. But if it's a number that's less than 7, like let's say 6, then that's going to make this be negative, right? And so we can't let that be negative because the graph of the natural logarithm function is always increasing, which means it always has to have a positive slope. Okay, so it couldn't come out to be negative. So this problem is one of the more challenging problems today, all right? And it's a question that's it could be asked on the AP exam, all right? Because it's challenging. It'd be one of the harder problems on the AP exam even, all right? So a line with slope m passes through the origin and is tangent to the graph of y equals ln of x. What is the value of m? All right, so you got to kind of picture what's going on, all right? So we have to know, what does the graph of the natural logarithm function look like? Okay, so I'm going to graph that first. Okay, so y equals ln of x. So it comes up along the negative y-axis. It's a vertical asymptote right there. Comes and turns and goes like this. Okay. Now, what do we know about this? We know that the line passes, a line with slope m, we know passes through the origin. So I know this is a point on it. Let me do it in a different color. So we know it goes through here. And we also know that it's tangent right here, okay? So this point right here is the point 0, 0. All right, and then this point right here has coordinates. Now this is gonna be weird. It's x, the x, right? And comma y, but y is really ln of x because that point is on the curve, right? So y comma ln of x. All right. So the slope, we're calling the slope between these 2 points m. So I know that m is equal to natural log of x minus 0 over x minus 0. So that means m has to equal ln of x over x. All right, what else do we know? Okay, we also know that this line is tangent to this, right? So I know the m can also be found by taking the derivative at this point. Now we just don't know what that point is, right? So we know that y equals ln of x. So then dy over dx has to be 1 over x being greater than 0, but that's the case here because it's on the graph, okay? And this is the slope at this particular x value, and I know it turns out to be m. So I also know that dy over dx at this x value is equal to m. So I also know that 1 over x is equal to m. So I know that the 1 over x is m. I also know natural log of x over x is equal to m. So these are both the same slope, so I can set them equal to each other. So what I have is ln of x over x must equal 1 over x. To solve this, what I could do is multiply both sides by x, as long as x isn't 0, which it isn't because it's over here, okay? So I'm going to multiply both sides by x, so that gives me ln of x is equal to 1. And then to solve this, I can exponentiate with base e. So this is e to the ln of x is equal to e to the first. E to the ln of x, they undo each other. So this gives you x is equal to e to the first, which is e. Now we're trying to figure out what the slope is, right? This will happen at this value of e right here. This is going to happen at e comma ln of e. Now I know the coordinates of that point, but that's not really what I'm trying to figure out. I'm actually trying to figure out what the slope is, right? And so this slope is 1 over x. Well, my x is e, right? So my slope must be 1 over e. And that's it. That's the answer to this. All right. So for this problem, we need to come up with a brand new technique, okay? So if y equals x to the x and x is greater than 0, that's this base right here, what's the derivative? Now, this is not the power rule because the power rule works when it's x to a number, okay? So power rule is when you have x to a number power, okay? And an exponential is when you have a number raised to the x power, all right? So we don't have either one of these, right? Because we don't have the number, right? We have x to the x. We have a variable in the base and in the exponent. So how the heck do you deal with this, okay? So we're going to start with writing y equals x to the x. And we also know that x has to be greater than 0. All right? So now what we're going to do is, and this is called logarithmic differentiation, is the problem is we got to get this exponent down out of that exponent. And the way we can do this is through logarithm properties. So what we're going to do is we're going to take the natural log of both sides. So ln of y is equal to ln of x to the x. Logarithm properties tell me that I can bring this power down in front. So this becomes the natural log of y is equal to x times the natural log of x. All right. So now because I've gotten everything out of there, all right, now I can take the derivative with respect to x of both sides. And that's how I'm, and because I have a y here, I'm going to pick up a dy over dx, which is what we're trying to find. Okay. So d dx of the natural log of y is equal to the derivative with respect to x of x times the natural log of x. So this becomes 1 over y, right? Because that's the derivative of natural logarithm function. It's 1 over whatever you're taking a logarithm of times the derivative with respect of your argument here, which would be dy over dx. So this is equal to the derivative with respect to x of x times natural log of x. So I have to apply the product rule. So the derivative of x would be 1. So this would be 1 times the natural log of x, and then plus x times the derivative of the natural log of x, which would be 1 over x. All right? So this is 1 over y times dy over dx is equal to the natural log of x plus, and this would just become 1. And now to get my dy over dx, I'm just going to multiply both sides of this equation by y. So multiplying this left-hand side would result in giving me dy over dx is equal to, and multiplying this side by y, this entire thing, now I'd have to use parentheses. So it's going to be y times the natural log of x plus 1. All right, and now I'm able to write this in terms of just x because I know what y is. Y is x to the x, right? And it's important that we say x it has to be greater than 0, and it's because of this right here. This logarithm right here, it has to be x has to be greater than 0 for all of this to work. So this y right here becomes x to the x. So my dy over dx winds up being x raised to the x power times the natural log of x plus 1. And my domain for this has to be x is greater than 0. All right? And that's the answer to this. That's the derivative of x to the x. It's x to the x times the natural log of x plus 1. Crazy, huh? Crazy, crazy. All right, let's do one more. So this is very similar to the other one. This is not an exponential because we have a variable in the base, but it's also not power rule because we have a variable in the exponent. So what we have to apply here is this logarithm differentiation, okay? And the x, again, this x has to be greater than 0 for this to work, okay? So once again, we have y is equal to x raised to the sine of x, and we also know that x is greater than 0. And so I'm going to take the logarithm. That's the key step here is we got to get this, and to remember what to do is we got to get this variable out of the exponent. And so what allows us to do this is by taking the natural log of both sides. So the natural log of x raised to the sine of x. And so the left side stays natural log of y is equal to sine of x times the natural log of x. All right, and now because I have a product, I can find the derivative. That's basically what I've done is I changed it into a product. All right, so I'm going to take the derivative with respect to x of both sides. So that's what I'm writing here. And then the derivative of this would be 1 over y times dy over dx is equal to, and then the derivative of this, I'm going to have to apply the product rule. So the derivative of sine x is cosine x times natural log of x plus sine x times the derivative of natural log x, which would be 1 over x. Okay, so now this becomes 1 over y times dy over dx equals, this is just cosine x, natural log of x, plus, and this is sine of x over x. Okay, now what I would do is I would get a common denominator here. So I'm going to multiply this, the top, there's a 1 underneath here that we're not writing, but I'm going to multiply by x over x to get a common denominator. So this is 1 over y times dy over dx is equal to x cosine x ln of x all over x, and then plus sine x over x. And that's going to allow me to write that as one fraction. And then I'm going to multiply both sides by y. So I wind up with dy over dx is equal to, I'm going to slide it up a little bit, y times, and then adding these together, we get x cosine x ln of x plus sine of x all over x. And then this y, once again, y can be replaced because y is the same as x to the sine x. So this is dy over dx is equal to x raised to the sine of x times x cosine x ln of x plus sine of x all over x. And that's the derivative of x to the sine x, or one way of writing it, okay? If you didn't get a common denominator here, you would just multiply this whole thing, and this would be, instead of having this on the inside, it would just be this. And that wouldn't be wrong, okay? All right, that's it, guys. That's logarithmic differentiation, and that's the last lesson of this unit. We are done with derivatives. Now we're going to start using derivatives to figure stuff out, like velocity and acceleration and speeding up and slowing down and all that other good stuff, okay? All right, guys, that's it. Have a great day.